welcome to the N3AS Room Seminar. We are glad to have Dr. Luke Jones to be our today's speaker. Luke is now the NASA Einstein Fellow at UC Berkeley, and he will talk about hydrogen mixing and the edge anomaly today. Luke, please take it away.
All right, so thanks everyone for being here. I'm sure many of you have seen talks before on the edges anomaly and its possible connection to dark matter. It's an interesting time to be thinking about this problem, I would say, because the dust has settled to an extent since the first round of proposed solutions. And what's emerged is that the initial explanations don't work out quite as seamlessly as one might wish them to. So there's reason to try new approaches. And so this talk will be about 21 centimeter cosmology. So in 2018, EDGES became the first experiment in this field to make a detection. It appears that they genuinely observed cosmic dawn, which is the turning on of the first stars. But their measurement has this anomalous feature I just mentioned, which is plausibly interpreted as indicating a much lower hydrogen gas temperature than expected. So I'll talk about a way to account for this anomaly that hinges on hydrogen oscillating into a dark sector state, H', and then losing energy to dark matter. So the mixing strength that's picked out by cosmology turns out to be at an interesting energy scale for colliders, as we'll see. And then finally, we'll discuss some interesting astrophysical implications besides the connection to edges. All right, so the field of 21 centimeter cosmology is premised on the fact that photons coming from high redshift CMB photons, for example, pass through clouds of neutral hydrogen on their way to Earth. So some photons are absorbed by the hydrogen, other photons are emitted by it. And for photons with wavelengths around 21 centimeters, absorption and emission are sensitive to the hyperfine structure of hydrogen. So just as a reminder, the hyperfine splitting, of course, arises because of interaction between the proton and electron magnetic moments. It's 21 centimeters as a wavelength or as an energy, 6 microeV. So to put the point maybe a bit simplistically, if all of the atoms are at the lower hyperfine level, then absorption is favored over emission. Because there are many atoms that can excite and none that can de-excite. But if you start to increase the fraction of atoms at the excited level, then emission becomes increasingly favored. Now the fraction of atoms at F equals 1 to atoms at F equals 0 is conventionally quantified by the spin temperature. Higher T sub s means more atoms at the upper hyperfine level. So just to say it again, absorption and emission tell you about the spin temperature. And the key insight is that the spin temperature in turn tells you about various processes taking place in the hydrogen clouds. And that's because T sub s is a weighted average of a few things, the brightness temperature of the microwave background, the kinetic temperature of the hydrogen gas, and the color temperature, T sub alpha, of the Lyman alpha radiation field. So the point here is 21 centimeter cosmology experiments, like EDGES, are aiming to infer the spin temperature of hydrogen at high redshifts so as to learn about the various processes that the spin temperature is sensitive to. And so again, in 2018, EDGES announced that they'd succeeded in this goal. The era of 21 centimeter observational cosmology has officially commenced. And intriguingly, it's already turned up an anomaly. So, so what did EDGES observe? This figure is actually showing the differential brightness temperature, which is closely related to the spin temperature, although I'm not showing the exact formula. But the message from this plot is that between redshifts of about 15 and 20, the EDGES signal shows a dip below 0 in the differential brightness temperature, which means that the spin temperature is colder than the background radiation temperature. That's a way to interpret this. And so seeing an absorption feature was not unexpected for reasons that I'll explain on the next slide. But the depth of the feature did come as a surprise, and the discrepancy is at the level of about 3.8 sigma. So let me explain why an absorption feature was expected, and then we'll discuss ideas that might account for it being anomalously deep. So this goes back to the goal of 21 centimeter cosmology, which is to observe the long period between recombination and the end of reionization. So during that period, the first stars start to turn on, rather, and again in this stage that's called cosmic dawn. And that brings to an end the period known as the cosmic dark ages. So cosmic dawn is also when the edges dip first starts to appear. So this dip here corresponds to the edges absorption trough we were just seeing. This dip is appearing because stars are injecting Lyman alpha photons that are indirectly coupling hydrogen atoms to one another. Basically, photons are bouncing around from atom to atom. And that drives the spin temperature away from the background radiation temperature and toward the much colder hydrogen gas temperature. So what I'm describing now is called the Waldheisen field effect. But then once enough stars have formed, their radiation begins to heat up the gas itself, and that terminates the absorption feature. So the important thing here is that the height of this absorption feature is at most the difference between the background radiation temperature and the hydrogen gas temperature. So with that in mind, now let's go back to this question: what could account for the anomalous depth? I mean, first of all, it's a complicated experiment, and foregrounds have to be modeled and so on. So maybe systematics are an issue. There has been discussion about that. But for the purposes of this talk, let's just say we believe the signal that EDGES is reporting. Explanations then mainly fall into two categories. Either there's unexpected astrophysics that's making the background hotter, for example, accretion onto early black holes, or the particle physics that's making the gas colder, for example, scattering between standard model particles and dark matter. So as many of you probably know, this last proposal has generated quite a lot of interest. The basic idea behind these kinds of scenarios, where you just have scattering between standard model particles and the dark matter, is that the baryonic gas, hydrogen, loses heat to dark matter, which is taken to be colder than the gas. This explanation was actually put forth along with the original detection announcement by EDGES. But here's the thing. So further study has shown that the explanation isn't quite as appealing as one might have hoped at first. It turns out that the simplest scenario is strongly constrained by fifth force experiments, because in the simplest kind of scenario, you could think of hydrogen has to have a net overall charge coupling it to a light mediator. So these scenarios end up being highly constrained. And an alternative is to let dark matter be millicharged, so it has some small electric charge, but it could only be a small fraction of dark matter that carries charge. And even then the scenario is highly constrained. So millicharged dark matter still works, I should be clear about that, but it's this state of affairs is kind of what led me and my collaborators to think of other possibilities. So I've been working on this with Seth Korn, who's a postdoc at Chicago. We've been thinking about a different kind of BSM scenario that we believe can achieve the same effect of cooling the hydrogen gas prior to cosmic dawn, and therefore might explain the EDGES anomaly. And one of our guiding intuitions is that, suppose EDGES does indicate new physics. We're thinking maybe it should be taken as a hint that the new physics has thus far only shown up in connection to neutral hydrogen. And one of the things that's special about neutral hydrogen is that it's neutral. So it can oscillate into a dark sector state without violating any gauge symmetries, much like how a standard model neutrino can mix with a stereoneutrino. Very similar kind of idea. Of course, hydrogen is also a composite particle, which means it's not totally obvious why there would be mixing between it and a dark sector state. But there is a well-explored model building framework in which this makes sense. It's the framework of mirror models, in which there's a copy of the standard model particle content. It's not necessarily all populated in the universe, but it exists. So these kinds of theories, they go back a long ways to Li and Yang in the 1950s, thinking about how to restore space-time parity as a symmetry. I believe they've been somewhat reinvigorated in recent years by work on the hierarchy problem and twin Higgs models. I'm not an expert on those topics, but Seth, my co-author, is. And so in any case, mirror sector particles interact with each other under their own interactions, which are mirror versions of the ones in our sector. So the simplest realization of this just has the sectors related to each other by a Z2 symmetry, which we're going to be assuming. So for example, the electron's counterpart is a mirror electron, which has a mirror electric charge. And because of the exact Z2 symmetry, has exactly the same mass. And likewise, there's a mirror hydrogen particle. And this is the dark sector state that we're proposing hydrogen mixes with. So as for the origin of this mixing, one possibility, which I'm going to return to in a few slides, is leptoquarks at perhaps the TeV scale. On being integrated out, these particles leave behind an H prime mixing term in the Lagrangian. So there's a lot more to say about other motivations for postulating mirror models and leptoquarks for that matter. But for our purposes, really, we're invoking them because they offer plausible underpinnings for hydrogen oscillations. And mainly what I'll be focusing on is the dynamics of mixing. Okay, so let's take it for granted then that hydrogen and mirror hydrogen mix with each other. There's somehow a term in the Lagrangian that accomplishes that. How exactly does this lead to cooling of the hydrogen gas? So first, H oscillates into H prime. We're going to think about this kind of schematically here. We assume that mirror hydrogen couples to dark matter, unlike standard model hydrogen. So then H prime scatters on dark matter, which is cooler, and that causes H prime to lose kinetic energy. And then it oscillates back into H, now carrying less momentum. So it's a kind of 2 or 3-step process. It involves both these ingredients, oscillations and scattering with dark matter. So to get a better idea of how that sequence that we were just looking at fits into cosmic history, let's return to the standard timeline. So here it's being presented slightly differently than it was before in order to emphasize how the individual temperatures are evolving. So first off, the radiation temperature, T sub r, is the CMB temperature. So at redshifts like 1/A, at redshifts above 200 or so, the hydrogen gas is thermally coupled to the CMB, but after that point, it just cools adiabatically. So Tg is dropping like 1/A squared. And initially, the spin temperature, T sub s, follows T sub g, due to collisions between hydrogen atoms. But after Z of about 40, collisional coupling becomes inefficient and T sub s returns to T sub r. So actually in the earlier timeline I showed, there were 2 dips. This is the first dip, which has not yet been observed by any experiments. Edges observes just this second dip, which is caused, as I was saying earlier, by astrophysical sources turning on and emitting Lyman alpha photons that then recouple T sub s to the gas temperature through the Waldheisen field effect. So, you know, what do we want to happen in the mixing scenario? We want the hydrogen cooling to take place sometime before Z of about 20, so that when the red curve dips down and reaches the green curve, it'll be at a lower temperature than the standard case predicts. It'll be lower than this this curve is showing. But at the other end, we can't have cooling occur before Z of about 200 because the gas and the CMB are still thermally coupled. So we'll end up seeing how these constraints show up in parameter space. And that means that the sequence from 2 slides back cools hydrogen somewhere in this redshift range, Z of about 200, and then Z of about 17 is just the kind of center of the trough. Peering back earlier, we just find the standard cosmology. We're assuming there's negligible H prime or mirror sector density. In the pre-recombination universe, hydrogen is all ionized and can't get through the mixing portal. But later on, and this is crucial, mixing stays in equilibrium past the edges signal and through reionization, so that as the density of neutral hydrogen drops, so does the density of mirror hydrogen. They're tracking each other because mixing is still in equilibrium. And so ultimately in this scenario, we expect most of the baryons that were lost through oscillations to be recovered by the end of reionization. All right, so let's do this. Let's estimate the energy scale of mixing that could make this timeline work. We actually do calculate things in a more sophisticated way than this, but you can this gives us the essence of the physics. So suppose that a hydrogen atom oscillates about 1 period between scattering events, sometime during the late dark ages. Well, then in other words, the mixing parameter delta, or the oscillation frequency, should be comparable to the hydrogen scattering rate at whatever redshift. So evaluating this at a redshift of about 30 tells us that delta should be on the order of about 10 to the minus 37 GeV. So I'm going to state the obvious here. This is a very small number. And so the mixing is going to be exquisitely sensitive to any physics that distinguishes between H and H prime. So on the one hand, this means that mixing isn't ruled out by any terrestrial experiments as far as we can tell, because any interactions, just having hydrogen in like a vat or whatever in a tank, any interactions will totally swamp the mixing term. But on the other hand, it means that H and H prime will have to be really just exactly equal in mass. And that's why we're using this Z2 symmetry, relating the standard model sector to the mirror sector. Okay, so we're dealing with a mass degenerate, non-unitary, 2-level quantum system. Delta, again, is the mixing parameter. Delta V is the potential generated by forward scattering in the medium. And the mixing really is described by a quantum kinetic equation for the density matrix rho. So that would be a 2x2 matrix. But we're not actually solving this. What we're doing is simply establishing that the timescales work out, because we're interested in a scenario where you achieve equilibration at the right times. This gamma os in particular is the mixing equilibration timescale. It's been used for many years in studies of sterile neutrino dark matter. But in fact, it's a rather general result from mixing, and it follows almost immediately from applying a certain kind of relaxation time ansatz to the quantum kinetic equation. So hydrogen's interactions are crucial in this scenario because they help to determine the timescale for mixing to equilibrate. They show up in gamma os. And so you can kind of read this as a table, and it's pretty simple. During the dark ages, the dominant process for both forward scattering and collisions is hydrogen-hydrogen scattering. But then that changes during reionization. The largest contribution to the collision rate switches over to photoionization. And then other processes are active, of course, but we show that they are all subdominant. So what we're doing is we're calculating gamma os and we're showing that at the appropriate times, it's greater than the Hubble rate for a range of the mixing parameter delta. In this figure, these three curves represent three different values of delta, just kind of representative values. And for all of them, mixing comes into equilibrium sometime prior to cosmic dawn, which would be, down there somewhere. And we are confining ourselves to what we're calling scenarios with minimal mixing, which means that the effects of H prime interactions on the mixing dynamics are always negligible. So this is going to put an upper limit on how large the cross-section can be between H prime and dark matter. But it keeps the dynamics simple and dependent only on one BSM parameter, namely delta. Okay, so let's look at the viable parameter space that we find for two choices of n, where n is the exponent in the velocity dependence of the H prime dark matter cross-section. We're picking a particular dark matter mass. I mean, there's actually a lot of flexibility in what dark matter can be, including what mass it can have. But this mass is singled out by just assuming that the heating that H prime and dark matter fully thermally equilibrate. So I'm going to comment on each of the sources of constraint in just a moment, but the main message is that if the mixing parameter delta and the H prime dark matter scattering rate both correspond to approximately cosmological timescales, then the full picture is consistent. So the scenario being presented here is one in which dark matter has a mass that's comparable to the hydrogen mass and a cross-section with H prime that's comparable to the H cross-section. And we're looking at values of delta that are in the neighborhood of 10 to the minus 37 GeV, which is what we predicted earlier. Okay, so in the region at the top, as I was just saying, H prime interactions do affect the mixing dynamics. They can. So on its own, this doesn't mean, being up here doesn't mean necessarily that the region is ruled out. And again, there is some flexibility in the nature of the H prime dark matter coupling, but typically larger cross sections are just going to suppress the mixing. So we're just excluding this from the analysis, I suppose I should say. In the region at the bottom, the cross section here is so small that heat transfer between H prime and dark matter is inefficient. You can get down to smaller values, notice if the cross section doesn't decline as velocities drop, but this cooling down is putting the lower limit on both cases. Then the bound on the left comes from needing mixing to be strong enough that it's still in equilibrium during the epoch of reionization. So in this region, H prime doesn't convert back to hydrogen. You'd have roughly half the baryon density in the present universe that you would expect. And then finally, in the regions on the right, but both up here and down here, both mixing and H prime dark matter heat transfer are occurring rapidly at redshifts above 200. But once more, since the hydrogen gas is still thermally coupled to CMB photons, heat from the CMB is just going to be channeled all the way through to dark matter. And so hydrogen won't actually be cooled in these parts of parameter space. Okay, so returning to this question of how mixing arises, we can connect delta to the scale lambda of new physics. So if we, working in terms of partonic degrees of freedom, the mixing operator is going to take this kind of schematic form. The primes are denoting mirror particles. And this is all very rough, of course, but we can map that to an operator in terms of hadronic degrees of freedom. And now just for the sake of specifying a plausible UV completion, let's, as I was saying before, suppose that these operators fundamentally arise from interactions involving leptoquarks. So an example of a diagram is shown here. And this is kind of the color coding we're imposing B plus L prime and B prime plus L as global symmetries and assigning charges to the leptoquarks in such a way as to avoid rapid proton decay and actually also to avoid near neutron oscillations. Specifying a UV completion also allows us to estimate delta in terms of the number of leptoquarks and their mass scale. And if we plug in a mass scale of a TeV or so, we're both in the neighborhood of leptoquark masses that are unconstrained by the LHC, or close to it, and also in the neighborhood of mixing parameters that are viable for explaining the edges signal. And so that's really just an interesting coincidence. So as I approach the end here, I'm just going to point to two final astrophysics tie-ins with this hydrogen mixing scenario. So the first is the missing baryons problem. Up until a few years ago, perhaps a third of all the baryons in the universe were observationally unaccounted for. They were expected to be there based on CMB measurements, and recent detections have been successfully locating many of these baryons, principally in the WIM, the warm hot intergalactic medium. But uncertainties are high on most of these measurements. And as far as we're aware, the hydrogen portal is the only proposed particle physics scenario that might predict that some of these baryons should be missing, if in fact mirror hydrogen doesn't completely reconvert to standard model hydrogen during reionization. The full calculation of doing that, you would actually need to solve the quantum kinetic equations, and it would involve structure formation and so on. So that's a challenging problem to estimate precisely how much remnant mirror baryons stay in that, are left after reionization. Okay, so that's one thing. And then the other is the formation of stars. So we expect that as gas clouds collapse during the dark ages, H prime mixing will shut off due to the high densities in the clouds. And at that point, standard model and mirror hydrogen will then evolve independently, except for the gravitational interactions between them. And so you can see that as you get to higher density, the oscillation time becomes longer than the gravitational freefall time. So presumably there's going to be some impact on the formation of the first standard model stars from having half the baryon density. But I actually want to draw attention to what happens in the mirror sector. So all we have in that sector is mirror hydrogen. And so the chemistry plays out differently. Ordinarily free electrons would catalyze the formation of molecular hydrogen, which is an important coolant in collapsing gas clouds. But we don't have these free mirror electrons. And so we suspect that the absence of H2 may lead to mirror gas clouds directly collapsing to supermassive black hole seeds. Because they're unable to cool and fragment into smaller stars. So this particular idea has actually been studied in detail in a couple recent publications. It's really just a coincidence that our scenario naturally links up with this work. And I should say the context here, of course, is that it's still an outstanding question how billion solar mass black holes got to be that big within the first billion years after the Big Bang. And then another possibility I'll just mention is the formation of mirror stars, and these two possibilities are not mutually exclusive. So we're not making any kind of rigorous predictions here, but we think that these outcomes are plausible at least. Okay, so to finish up, I'm going to return to this slide I showed at the beginning. Again, the overarching question here is how to explain the edges 21 centimeter anomaly. And the proposal I've been discussing is that the super adiabatic cooling of the hydrogen gas is facilitated by mixing between hydrogen and this mass degenerate dark sector state. Okay, so I'll go ahead and end there, and thank you all for your time.
Okay, thank Luke for the nice talk. So Susan has a question about the magnetic field. Susan, would you like to ask by yourself?
Thank you very much for letting me do so. Yes, I have worked a lot on neutron anti-neutron mixing and on oscillations with neutrons and antineutrons. And so this is a very interesting scenario from my own interest. What I just wanted to point out is that if we think about neutral hydrogen, because the electron magnetic moment is 2,000 times larger than that of a proton, that it has a sizable magnetic moment, and we can anticipate just through motion of the hydrogen in these early clouds that we could expect ambient magnetic fields. Those magnetic fields generically will generate Zeeman splittings of the F equals 0 and F equals 1 hyperfine levels that you've indicated. Now, this is important because certainly the electromagnetic moment is numerically very large, and we can expect that these splittings of neutral hydrogen will be so numerically significant that they would normally suppress HH prime mixing. So much so that I'm not sure that the kinds of mixing parameters you discuss as being pertinent are actually accessible. And so my question was to point out this issue, that it may just imply that you should have a richer mirror sector, that maybe there are mirror magnetic fields you have to consider. I'm not sure, but certainly if you only have mirror matter that's degenerate to hydrogen in the absence of magnetic fields, then I do think you would have a problem. So anyway, so I think this is a comment and a question.
Yeah. So this is a great point. And the magnetic field strengths in the IGM today would easily swamp the mixing by many orders of magnitude. And so what we do in the paper is we, kind of report the kinds of numbers that people find for magnetic field strengths prior to reionization, just based on standard cosmology and astrophysics. We show that if that's what we're adopting for the source of magnetic fields today, then we're safe, or at least kind of on the border. I mean, it's an interesting area for further exploration, but the history of magnetic fields, even in the standard scenario, is very uncertain. So this is an important assumption that we're making, because many theories of magnetogenesis involve non-standard physics. And so this BSM scenario would be incompatible with many of them. Many of them might produce magnetic fields at inflation.
Your assumption is that there are no magnetic fields operative.
Our assumption,
is that correct?
Our assumption is that the magnetic field strengths is that the magnetic fields form from standard cosmological and astrophysical processes, that they're not produced from inflation, for example. We're not assuming any kind of primordial magnetogenesis.
But the dynamics of a hydrogen cloud in and of itself would normally generate some kind of magnetic field, because you have these little electromagnetic moments. Each hydrogen atom can be thought of as an electromagnetic moment, and the cloud is tumbling.
I mean, yeah, right.
In your original assessment of the spin temperature, there was a collision term. So it seems to me, as long as I have kinetic mixing of the hydrogen atoms, I get to generate some maybe very small magnetic field. But since your deltas that you want are so very small, I'm thinking it's very easy to swamp that effect. So I'm just pointing out to you, I haven't run the numbers, but I'm remarking, I'm just thinking in a scenario where I have standard model magnetic fields, because my electromagnetic moments are big and my hydrogen atoms are tumbling in the cloud, even a cold cloud, then I would normally seem to have some kind of ambient magnetic field. And therefore, I think I'm quenching HH prime mixing. And that's my point to you. And so I'm just saying, I believe there's a standard model effect. The generated magnetic field might be small enough that you're safe, but since you want to have such a small delta, then I think it might be very hard to arrange the conditions to actually have that's I think I said my thought, so I don't mean to berate it. Let other people ask questions. I just wanted to plant that seed of thought.
Yeah, well, I do just want to say, so this is something we thought about quite a bit. And what I was saying before is that the history of, I'm kind of getting a lot of feedback from someone's computer, I think. The history of magnetic fields in the IGM is highly uncertain, but in standard scenarios, the magnetic field strength is not high enough pre-reionization to make this scenario inoperative. You're kind of pointing to a related but different effect, which is that magnetic fields do start to form within collapsing hydrogen gas clouds. That's different from what happens in the IGM. In collapsing hydrogen gas clouds, it's true that the formation of magnetic fields will also act to shut off mixing in much the same way as the increasing density will. So this is a question that this is something we point out but kind of punt on, and ultimately this will be related to how much of the mirror sector density is protected from reconversion during reionization.
Yes, I guess that's a separate point, isn't it? That if in fact the ambient magnetic field is changing over time, then that if in fact you oscillate to H prime, and in the meantime, the magnetic field has somehow altered, you might not be able to oscillate back into H. I guess that's what you're saying, yes?
Mm-hmm.
Okay, well, I just wanted to raise the issue, and thanks.
Okay, Shaud has two questions. Shaud, would you like to go ahead?
Yeah, these are very basic questions. One of which is, so you talk about mirror hydrogen oscillating, but I don't quite understand the particle physics to know why. I mean, do you need the entire hydrogen atom to oscillate at the same time, or are there just separate oscillations for electrons and protons that on bulk would conserve charge?
Right. So we actually do need the whole hydrogen atom involved in the particle physics model that we're specifying. You can think of it as being like, this is a kind of passageway from a standard model hydrogen atom into a mirror hydrogen atom. And if you were to kind of take out certain parts of this, like maybe you just want two standard model quarks to go to two, if you wanted something, you in principle, you could have, let's say, neutron, mirror neutron conversion, or you could have neutral mesons converting into the mirror sector. Those are being prohibited by the requirement of preserving these symmetries. So this is baryon number in the standard model sector, baryon number in the mirror sector, and then similarly for lepton number. And you couldn't have something like, so charged particles are already off limits because of the gauge symmetries. So a mirror electron has a different kind of charge than a standard model electron.
Okay. And the other one is you mentioned this as a possible explanation for missing hydrogen, presumably because the hydrogen would have oscillated into this mirror hydrogen, which we don't observe. So this problem of missing hydrogen, is this just maybe I don't understand this missing hydrogen. Is this missing hydrogen effectively dark matter because it's just hydrogen that we can't see, or would explaining this missing hydrogen as oscillated mirror hydrogen require us to to have more dark matter than we observe?
So the missing baryons problem, I think a lot of people would say is resolved or on its way to being resolved. So we're not actually proposing a solution to this problem. We're just suggesting that there is an interesting connection here. There's kind of like this many years long enterprise, observational astronomy enterprise of trying to pin down exactly where all the baryons are. We know what to expect based on CMB measurements. we know what the baryon density today should be, and then you can just kind of like go and look for baryons in different states and different places, and try to account for all of it. So it's a kind of census in the present day that should match to the early universe.
Okay, so that you would say there aren't missing baryons, but the story could be complicated by this.
Yeah,
okay.
Something like that, yeah.
Okay, George has a question.
Hi, Luke. Great talk. Thank you. My head is spinning. So the spin temperature of my head has gone way up. Thank you very much. So a couple of questions. For one thing, of course, in addition to some tiny mixing, there is, of course, complete gravitational coupling with some mirror sector. So, and this immediately begs the question of what the dark matter is. The dark matter number, the fraction of non-relativistic contribution to closure is very small. It's right. It's only something like 4 or 5% of the closure density. And so, the rest of the dark matter could well be produced in much the same way. This asymmetric dark matter idea, right? They only differ by a factor of 5. And so that immediately begs the question of whether there's something in the dark sector that does that. So, if there are dark baryons in this sector, we see them gravitationally. They're part of that closure parameter. You can't get around it. It's just the gravitational coupling. So you pick out a mass that's sort of an interesting regime of 2 GeV, which sounds like a mirror deuteron. So comments on that. I mean, could we have the dark matter actually be in this other sector? There's something different, right? If whatever asymmetry arises is, 5 times larger in the dark sector than it is in the standard model sector.
Yeah, so short answer is I don't know. I will say this: what we kind of had in mind for dark matter is something like the following. We kind of have 2 asymmetries here between the standard model sector and the mirror sector. One is the fact that there's dark matter in the mirror sector. We're kind of assuming that. And then there's all the standard model stuff that we have in our sector.
Do you really need that, though? I mean, could it just be that these that the dark matter, the non-relativistic contribution to closure, the so-called dark matter, is just the baryons in this these mirror baryons?
Right. So, and George, would you mind just muting yourself while I'm talking? I'm kind of getting feedback, if you wouldn't mind. So all I'm saying is that one way to think about this is you could have a sort of like this is a background statement to exploring the idea you're suggesting. You could have something where it's like you have an inflaton or 2 inflatons, a standard model one and a quote unquote standard model inflaton and a mirror one. And then maybe you also have an axion-like particle in each sector. And in both cases, just through kind of like, it'd be something like the misalignment mechanism for the axions, and just, it's kind of like random chance. You happen to have the axion field arranged in a way that you produce all the standard model stuff we see, but you don't really produce any of the dark matter stuff, except that the axion is its own field, and it happens to be, in a position where it gets produced in the dark sector, but not the standard model sector. In other words, one way to work this out is just thinking in terms of like introducing scalar fields or something like that. Now you're suggesting we just kind of start with all of the standard model stuff and try to kind of bootstrap it, I think, right? Like you have maybe 2 different oscillation channels. And I have to say, I haven't thought that much about this, but I'm intrigued.
No, I'm actually suggesting that, if you're saying that the mirror mere hydrogen, mere proton is effectively almost identical in mass. Not quite. There's some small splitting. That suggests there are differences between the mirror sector and the standard model sector, which is okay, that's fine. And I'm also suggesting that the dark matter, whatever it is actually kind of comparable, it may be in its production history, to the baryon symmetry in the standard model sector, just the asymmetric dark matter idea. So I'm just wondering whether you need, whether it's just, what kind of, let me put it this way. Can you get away with a sort of standard nuclear sort of interaction cross-section at these energies in the mirror sector to do your, your anti-hydrogen, quote unquote, anti-hydrogen dark matter scattering?
Yes. I mean, the answer to the last part is yes. But I don't know that, so I think we are saying the same thing in terms of kind of like trying to take advantage of the baryon asymmetry. And so ultimately the dark matter is also connected to standard model stuff in the same way that H prime production is connected to standard model stuff. I haven't thought about whether a scenario could be made, could be devised that achieves what you're talking about.
Thanks, Luke.
Okay, so Wick has a comment regarding to Susan's question. Wick, would you like to discuss it?
Oh, sorry, I should have made that private to Susan. I screwed up there. I just wanted to mention that there's been some nice atomic work on scenarios where the spin temperature and the real temperature diverge. But I think the paper I remember is so old, it's at least 4 or 5 years old. It was probably pre-edges, so they may not have looked at this scenario in detail.
I had some, we have a research assistant professor at Kentucky by the name of Mario Choksixos. I'm not going to say his name quite right, but he works with Rick Gary. He's within the aegis of Gary Furlan's group, and he is quite the expert on computing the effective spin temperature in cold hydrogen clouds. They had their own interest in those issues. Certainly the effective spin temperature is determined by a number of dynamical points within our own galaxy. Lyman alpha radiation is important on the cloud, as well as collision of hydrogen atoms within the cloud and potential admixture of metals. Not all of those features would be operative in this high Z scenario that we've heard about today. But nevertheless, I guess I was part of this interest, and the impact of magnetic fields was derived from my discussion with colleagues on these more complicated points. So I guess I'm intrigued at the idea that ordinary magnetic fields within the cold hydrogen cloud itself don't shut off these dynamics. But if you've looked at the effect and tried to compute the numbers and think it's not an issue, then very well. But I'm a little surprised, frankly. But I just wanted, there is this broad, rich context of how we understand the dynamics of clouds. And actually, Marios had told me how interested he was in the edges effects, because he thought that maybe there were aspects of it, just the dynamics of these structures that we didn't fully understand, and that they might be operative in the edges anomaly. But I haven't, unfortunately, COVID has shut down all the casual conversations I used to enjoy with colleagues. And so if we were back in our offices, Marios is 2 doors down from me. I would knock on his door and say, hey, what happened? But unfortunately, I don't know. And so maybe I should just drop him a line and see what he was, what's come out of his interest in edges. So thanks though, Wick, for mentioning that.
Okay, thanks, Susan. And let's thanks Luke again for his nice talk. And we will see you again after 2 weeks. Thank you.
Thanks, everyone.
Thank you, Luke.